Hello, let's take a look at stoichiometry once again, except we're going to examine stoichiometry as it's applied to gases. Before we take a dive into some problem solving, let's take a look at some strategies. You saw a version of this previously when we were solving regular mass-to-mass stoichiometry problems. So as a matter of fact, most of this map is familiar to you. Start with the grams of substance A. And we assume that the chemical reaction is, say, A being converted to chemical B. We start with a mass of grams of A. To convert from grams of A to moles of A, you would divide by the molar mass of whatever substance A is. If you wanted to solve for the grams of B, you would continue going straight from left to right in the map. Convert from moles of A to moles of B by multiplying by the mole ratio of substance B over A. And then once you have solved for the moles of B, multiply by the molar mass of substance B to get the grams of B. All of that is at the heart of stoichiometry, and you very well might still be solving for mass to mass stoichiometry using gases. However, because gases are more easily understood in terms of volume, as a matter of fact, volume and mass stoichiometry is much more common when gases are involved. So let's pretend that instead of being given the mass of gas A, you were told the volume of gas A, and that volume is in liters. Well, you can convert from volume of gas A to moles of gas A. There are two specific strategies. If you are told that the gas is at STP, you can simply take your volume of gas A and divide by 22.4 in order to get the moles of gas A. That's super simple. If the gas is not at STP, use the ideal gas law. Since you have to solve for N, that particular form of the gas law would look like pressure times volume divided by R times T in Kelvin. So rearrange the gas law, solve for N. That will get you to moles of A, and then you can proceed on to solve for moles of B. Similarly, if you're trying to solve for volume of B in liters, once you have the moles of B, you can multiply by 22.4 if the conditions are at STP. If they are not, use the ideal gas law to solve for V. So that particular variant of the gas law would look like nRT divided by P, where N is the number of moles of B. So whether you are at STP or not, there are multiple ways in which you can solve for volume of gas B, or if you are given the volume of gas A, you can convert that to moles of gas A pretty easy. Now, before we move on, know that there are some shortcuts that exist, but be very careful with these shortcuts. Whenever I say shortcuts, kids cheer. Well, they should because they're pretty awesome. But you have to know that there are some conditions where you cannot use shortcuts at all. So the tricky part is in knowing when to use these shortcuts and when not to. So shortcut A applies if your problem explicitly states everything is at STP and the conditions stay at STP. So if those conditions are at STP throughout the problem, you can use 22.4 liters is equal to 1 mole. That very easily helps you convert between volume and moles without having to use the ideal gas law. If the problem entails volume to volume stoichiometry, meaning you have a volume of gas A, I want you to convert to volume of gas B, and the conditions are at STP or the conditions are not changing, here's a fun trick. You can do mole-to-mole stoichiometry as if the volumes were moles. In my opinion, I think that takes some finesse. Like you have to realize that this is a volume-to-volume problem and that the problem is at STP. If you are feeling like not confident about your abilities at this point in time, which is totally okay if that's your situation, you do not have to use either of the shortcuts. You can always use regular dimensional analysis stoichiometry or even the proportions method, which does work for gas stoichiometry problems. So let's take a look. So, in all of these problems we're about to do, we're just going to use this very simple balanced chemical equation. I do mean balanced. You have to balance the equation if the chemical equation given is not balanced. But we're going to use this chemical equation in our stoichiometry today. We are told we have 15.0 liters of oxygen gas at STP. I like where this is going. It's reacting with excess hydrogen. We want to calculate the volume of water vapor produced. So let's use shortcut A. And this is just to use that relationship 22.4 liters is equal to 1 mole of any gas, or in this case, oxygen gas at STP. So 15.0 liters of oxygen gas. We're just going to divide by 22.4 liters per 1 mole of oxygen gas. So what this will do is this will help us understand the number of moles of O2. And then since we are seeking a water vapor, our mole to mole ratio is not 2 here, 1 here, 1 to 2. This means that we're going to put 1 mole of O2 in the denominator here and 2 moles of water up here. That will get me to moles of H2O. And from here, since we're looking for volume, since there is no mention of STP changing at all, we're just going to use the same relationship, 22.4 liters is equal to 1 mole, but of water instead of oxygen. So solve, and then realize that 22.4 also cancels. So we get 15.0 times 2 divided by 1, which is 30.0 liters of H2O. So that is our volume of water vapor produced. If you're curious, you could also do the proportions method with this. So the way this works is to take 15.0 liters of O2, realize that the coefficient for the oxygen gas is 1, so this means 1 mole of oxygen gas. We know this is at STP, so 22.4 liters over 1 mole will equal 22.4 liters is equal to 1 mole. So that's our work on the left-hand side. On the right-hand side, we're solving for the number of liters of water. The coefficient of water is 2 moles of water. And we, again, still use this relationship, 22.4 liters over 1 mole. So that moles cancels in this way. So cross multiply, so this would be 15 times 2 times 22.4, but that would be divided by 22.4. So actually the 22.4 would still cancel out. So in the end, we get 1 times x is equal to 15 times 2. Therefore, x is 30.0 liters of water. So absolutely, you can do the proportions method in this way for gas stoichiometry. As you can see, you get the same answer. Here is the second of 3 ways to solve this problem, and this is shortcut B. It's the same problem, 15 liters of oxygen gas at STP, still remaining at STP. We need to calculate the volume of water vapor produced. This is a volume to volume problem at STP. So we can work with volumes as if they were moles. So this means 15.0 liters of oxygen gas times, let's see, I have, for every 1 mole of O2, I have 2 liters of H2O. So I'm just going to multiply this by 2. And so I get 30.0 liters of water. That's it. That's shortcut B. Again, that only works because this is a volume to volume problem. You probably noticed from the previous slide that 22.4 liters canceled themselves out, and that's why this particular shortcut works. This simply represents the kind of a quicker way of doing the same strategy. Let's take a look at a third way to solve this problem. That would be for folks that just want to see every single step laid out. The third way to solve this problem is not to use the shortcut 22.4 liters equals 1 mole of gas. Instead, you would just be using the ideal gas law. It is slower, but for people that might feel like they need to see all the steps, this might be the way for you. So 15.0 liters of oxygen gas at STP reacts with hydrogen gas, so we're going to need to solve for the moles of oxygen gas. So the moles of oxygen gas is going to be the pressure times the volume divided by R times T. The pressure at STP, actually, we're not given a pressure unit, so we could use any pressure unit you want. Let's use kilopascals. Why not? Standard pressure would be 101.325 kilopascals. So I'm going to put in 101.325 kPa. The volume is 15.0 liters. All over, we're using 8.314 for our R unit today. And that's going to be multiplied by, standard temperature is 273 K. So Kelvins cancels, kPa would cancel, liters would cancel. In the end, we'll get moles out of it. So the number of moles of oxygen is 0.6696. So once you've figured out the number of moles of oxygen, we can then do really simple mole-to-mole stoichiometry to figure out the moles of water. So we're going to take 0.6696 moles of O2, and we're going to use the mole-to-mole ratios. For every 1 mole of oxygen that reacts, 2 moles of water will come out. So we're going to multiply by 2/1. So the number of moles of water that should result would be double. So we're going to multiply 0.6696 times 2, and we get 1.339. You'll notice I'm being super lax with sig figs right now, but that's because we are not near an answer. 1.33926 moles of water. We're trying to solve for volume. So again, if you're not into using the shortcut 22.4 liters equals 1 mole, you're going to have to use ideal gas law for that. So number of moles of water would be, again, P. Actually, we're not solving for moles of water. We're solving for volume. Sorry. So volume of water is going to be moles of water times R times T divided by P. Moles of water is 1.33926 moles. Times, we can use kPa again, so 8.314 liters times kPa over mole K, times temperature is, again, 273 K, since it is still at STP, and divide by 101.325 kPa, because it is, again, at standard pressure. So when you solve for the volume of water, you will get liters, and the answer is exactly 30. I have 3 significant figures, so I'm just going to put 30.0 liters as my answer. So that's how to solve the same gas stoichiometry problem 3 different ways, all 3 of which are perfectly valid. Of course, this last way is a lot longer and slower. So that the value of that shortcut, 22.4 liters equals 1 mole, is super useful, especially on a test where you may not have all the time in the world to solve the problem. So whenever the problem talks about things being at STP, I would jump on that shortcut and make the most use of that shortcut to help you get the correct answer. So what if the problem describes a situation not at STP? You're going to have to use the ideal gas law. There is no way around it. Use that to convert between moles and volume. To do the actual stoichiometry part, you need to get the number of moles, and you will not be able to use 22.4 liters. So exert a lot of caution. Because kids know that this shortcut exists, they want to use 22.4 liters all day, every day. The reality is it only works if the problem states flat out that the thing is at STP. So let's take a look at problems where you do not have 22.4 liters to fall back on. Okay, so we have 10 grams of oxygen gas. It's at 30 degrees Celsius, 1.10 kPa. That should be ATM, not kPa. Sorry about that. We're going to calculate the volume of water vapor produced. Right away, you should note this is not STP conditions, since that would be 273 K and 1 ATM, and we're not at either of those conditions. Right away, we can convert this temperature to Kelvin, so that would be 273 plus 30, which is 303 K. That's going to be our temperature. We have no information as to the moles of oxygen gas, but we could solve for it since we are told that there are 10 grams of oxygen gas. So we can solve for N right now. N for the oxygen is going to be 10.0 grams divided by the molar mass of oxygen, which is 31.998 grams. So 10.0 divided by 31.998, which is 0.3125. So there's our N value, just as we have our T value, and we have the pressure given. So we can go ahead and use this number of moles of oxygen gas to figure out the number of moles of water. So 0.3125 moles of O2. We're going to need a mole ratio between O2 and water. So there's 1 mole of O2 for every 2 moles of water. So we're going to multiply by 2 over 1. So just multiply 0.3125 times 2, and you get 0.6250. So now let's figure out the volume of this water vapor. So we're going to manipulate PV is equal to nRT. So volume is going to be nRT divided by P. That N would be the 0.6250 moles that we just calculated, since we are interested in the volume of the water after all. R, since we're using ATM, we're going to use 0.0821 liters times ATM over mole K. And the temperature is 303. All that's going to be divided by the pressure, which is 1.10 ATM. And so our volume of water will be, I get 14.134. So 3 significant figures from all of my data means that I'll have 14.1 liters as the final answer for the volume of the water vapor. The other way to solve the problem entails the proportion method, but realize that it's not actually much of a change when we compare this method versus the previous slide, because you still have to solve for the moles of oxygen. That's still important. So N of O2, I believe, was 0.3125 moles. So you would just solve for the moles of oxygen gas in the same way as we did before, just divide by the molar mass of oxygen. From here, if you wanted to use the proportion method, 0.3125 moles of O2 divided by the coefficient of O2, which is 1, equals X moles of water, since we are trying to find the volume of water, divided by 2 moles of water, since that is the coefficient from the balanced equation for water. So you would cross multiply. So you would get 1 times X is equal to 0.3125 times 2. And you still get 0.6250. And then from there, since that's your N, you would just use V is equal to nRT over P, just as in the previous problem. Just again, make sure that you sub in the correct value of N. N would be 0.6250. I'm not going to write it out all here, but you would still get 14.1 liters as your final answer for the volume of the water vapor. Finally, it is completely possible to have to deal with percent yield and theoretical yield and actual yield. So taken from the previous situation, we have the 10 grams of oxygen gas under these conditions. Let's say someone were to actually perform the experiment and they actually produce 13.8 liters, but the theoretical yield, which is the yield you calculate as being the amount to expect, is 14.1 liters. So you can solve for percent yield as if these were grams. Just realize that you're using volumes instead. So 13.8 liters is your actual yield. Your theoretical yield is 14.1 liters. Multiply by 100%, and you get 97.9% yield. So that's not much of a twist. We're just using that same percent yield formula of actual over theoretical times 100% to solve. Instead of using grams, though, we're using volume. So that's a rundown of how to solve gas stoichiometry problems. I will be dealing with limiting excess situations in the next screencast, but for now, I hope that this is enough for you to get started. If you have any questions or need any help, please feel free to reach out.